This is the optimized structure of chloroethane, showing two of the important bond lengths in angstroms. We also have labeled the alpha carbon, that is the carbon to which the chlorine atom is attached by the 1.824 angstrom bond, and the beta carbon is the carbon that is neighboring to the alpha carbon and is directly bound to it. Circled in green is one of the hydrogens that is attached to the beta carbon, therefore it is a beta hydrogen. Here is the second beta hydrogen, and there is a third beta hydrogen eclipsed behind this hydrogen, also attached to the beta carbon. Because there is free rotation around this carbon-carbon single bond, any of the three beta hydrogens could conceivably be in the anti-periplanar position necessary for the E2 elimination reaction. This is the computed transition state for the elimination reaction of the very strong base hydroxide acting on chloroethane, abstracting the beta hydrogen that is anti-periplanar to the leaving group of chlorine. Notice that the green atom, chlorine, the two gray atoms, carbon, and the alpha hydrogen are all in the same plane. That makes them periplanar. The anti part is that the chlorine atom of the leaving group is pointing to the left, whereas the beta hydrogen is pointing to the right. Since they're pointing in opposite directions, that makes them anti. So they are anti-periplanar. Here we have added Lewis dots to represent the single bonds that are important in the E2 elimination reaction: the carbon-chlorine single bond, the carbon-carbon single bond of the alkyl halide, and the hydrogen-carbon single bond connecting the beta hydrogen to the beta carbon. And last but not least, we have the crucial lone pair on the base of hydroxide, which ultimately abstracts the hydrogen from the beta carbon. Electron pushing arrows show the flow of electrons. From right to left, we have the lone pair on the base, abstracting the beta hydrogen. So we have a line going from the lone pair on the base and a curved arrow pointing directly to the beta hydrogen, because we're going from where there's a surplus of electrons to where there's deficiency of electrons. Then in the middle, we have the pair of electrons connecting the beta hydrogen to the beta carbon move into add to the carbon-carbon single bond to make it a double bond. And to the left, we have the pair of electrons leaving with the leaving group chloride as it departs. In this side view of the transition state, we can clearly see the anti-periplanar arrangement of the chloride leaving group and the beta hydrogen that is abstracted by the base. The major product of this reaction is ethylene, which features a carbon-carbon double bond in the place of the carbon-carbon single bond of chloroethane. Here is the optimized structure of 2-chloropropane, which is a secondary carbon as opposed to the primary carbon that we saw in chloroethane. Here is the computed transition state for the E2 reaction on 2-chloropropane, showing the leaving group of chloride attached to the alpha carbon. And notice that in this molecule that there are 2 carbons that are directly connected to the alpha carbon, which means that we have 2 beta carbons. Attached to those, we have a total of 6 beta hydrogens. And we see in this particular transition state that one particular hydrogen, the one that is connected by the dotted lines to the base, is the particular beta hydrogen that has the correct orientation to be abstracted in the E2 reaction. Here we've added dots to show the important electron pairs involved in this E2 reaction. E2 is a concerted reaction, which means that all the flows of electrons displayed occur simultaneously. From left to right, we have the lone pair on the base, abstracting the beta hydrogen. In the middle, we have the bonding pair between hydrogen and carbon, shifting into the carbon-carbon single bond to turn it into a carbon-carbon double bond. And we see the bonding pair between the alpha carbon and the leaving group chloride, leaving as a lone pair with chloride, thereby breaking the carbon-chlorine bond. In this side view of the transition state, we can see the anti-periplanar arrangement of the leaving group chloride to the right, following through 2 horizontal carbon atoms, as well as just to the left, the beta hydrogen involved in the reaction. And they are all in the same plane and anti-oriented. Here is the computed structure of tertiary butyl chloride, which is a tertiary carbon. Recall that for E2, tertiary carbons are more reactive than secondary carbons, which are more reactive than primary carbons, and that methyl carbons do not undergo the elimination reaction. Notice in tertiary butyl chloride that we have 3 beta carbons attached directly to the single alpha carbon, to which is bound the leaving group of chloride. The product of this reaction is 2-methylpropene, also known as isobutylene. Here is the computed structure of isobutylene, along with the relevant bond lengths in angstrom. Notice that when we see a bond length on the order of 1.50 angstroms, that is what we associate with a single bond, whereas when we have a bond that is 1.335 angstroms, that is consistent with a carbon-carbon double bond. Here we have added Lewis dots to also reinforce the notion that the 1.5 angstrom bonds are single bonds, whereas the 1.335 angstrom bonds are consistent with double bonds. This table summarizes numerically the results of the investigation into the transition states of these 3 particular E2 reactions. It's curious to note how the bond lengths change, that the carbon-chlorine bonds get longer as we approach the transition state. The carbon-carbon bonds get shorter, as well as the carbon-hydrogen bond getting longer. The only bond lengths that are shown for the products are the resulting carbon-carbon bonds, which have gone from being single carbon-carbon single bonds in the alkyl chloride to being carbon-carbon double bonds in the alkene products. Thank you very much for your attention. Have a good one, as always.